Okay, the next video, I'm going to combine these two reactions together because my videos are getting very long. So we're going to talk about condensation and hydrolysis reactions, which they are the reverse of each other. So let's start with condensation. Condensation, is there any definition that we can use here? So to reduce to another denser form as a gas become dense. Anyway, so basically you make more dense and compact. I think make more compact is probably a good definition that we can use here. And more specifically, in the context of easy chemistry, the condensation reactions will happen and you're going to condense or combine two reactants by removing H2O. Not the only type of condensation reaction that can take place, but the only type that you need to worry about this year. Okay. Oh, I should have used this to make dense. I don't even know what this is for. Okay, anyway. So a condensation reaction is a reaction in which two molecules are linked together and a H2O molecule is eliminated. So I think essentially if you can find where the H2O comes from, that's like already 75% of the reaction, and then you just combine whatever's left. Two products will be created from the reaction. You're going to combine the residue of the two reactants as well as you're going to get a H2O. The only type of condensation reaction that you need to know this year, thanks to the reduced curriculum, is esterification, or the condensation reaction between a carboxyl group, so carboxylic acid, and a hydroxyl group, so an alcohol, to produce an ester. And the catalyst, and you definitely do need to know this, is concentrated sulfuric acid. We may do this in class. I know you loved this activity last year when you make ester and then smell it. Okay, so let's talk about this. This is just year 11. I think the other two types of reactions were year 11 too, but somehow it doesn't seem like it. So let's say I need a condensation reaction between methanol and propanoic acid. So let's just start with the drawing of methanol. So this is methanol. It has one carbon. It's an alcohol, so it has a hydroxyl group. So that's methanol. And I'm going to use another color for the carboxylic acid. So propanoic acid, 3 carbon, including the one that is part of the carboxyl group. There's 2 H here, and then H, H, and H. Okay. So because this is a condensation reaction, I think the most important thing is to understand where the water comes from. And the carboxyl group is going to donate the OH, and the hydroxyl group is going to donate the H. So the water, actually the OH comes from the carboxyl, and the H comes from the hydroxyl. Okay, so the H is going here. So that's your water. Now, if the question asks for structural formulas, make sure that you draw the water in structural form as well, and you need H2SO4 concentrated or liquid as the catalyst. Whatever is left is going to form the ester. So this O, it's going to go and form a covalent bond with this C over here. So I'm not sure whether I can fit this in, but let's hope. I may have to do the, no, I'm not gonna have, all right, let's put the water, the H2O down here. So that's the H, and then there's a C. I shouldn't have, that gap was unfortunate. Okay, and then there's a O here, and then the rest of the carboxyl. Now obviously it means that you have to flip the orientation of the carboxyl, but you're gonna be fine, you can do that. Okay, let's put OH here. So this O is now linked to this C, double bond O, and then I'm just drawing the rest of the carboxyl. So you have the O, C double bond O bond, which is your ester. So C, H, H. So this is the ester linkage that has been formed. And the name of this ester is going to be methylpropanoate. Now, the reason why I picked these two is because I want to point out the difference between the reaction between methanol and propanoic acid and the reaction between propan-1-O or propanol, well, propanol was more accurate, and methanoic acid. So let's talk about the second one. The second one, you only have one carbon in the carboxyl group. Let's try not to make the same mistake. So I'm going to try to create more room for the product. So COOH. Methanoic acid is always a funny molecule to draw for a lot of people because it looks really small. But this is it. It has one carbon. Okay, and then the other one is propan 1O. Obviously, you can have propan 2O, but let's talk about that next term. You don't have to name it though. So this is propan 1O. The hydroxyl is on terminal carbon or carbon 1. So similar things will happen in the second reaction, except that your product is propylmethanoate and not methylpropanoate. So I'm not speaking English. Okay, so this H here, and then this OH will combine to form water. So you're going to have the H from the alcohol or the hydroxyl group, and you're going to have the OH from the carboxyl group. Okay, you need H2SO4 as the catalyst. Now whatever's remained, I'm going to draw the carboxyl group first, sorry, the hydroxyl first, or the residue of the alcohol. So C, 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 and then you have an O here. Let's draw all the H out so no one can accuse me of being lazy for not drawing hydrogen. Not that I would ever do that in notes anyway. Okay, so that's that, and then basically this O is gonna go and combine with this C. I don't know why I had to draw that. Okay, so that O is going to combine with that C, double bond O, and there's still a H there. It doesn't go anywhere. So there's your ester link again. Let's put a plus here. Okay, so that's esterification. Is there anything else? Okay, so the opposite of a condensation reaction is a hydrolysis reaction. It's literally the reverse reaction. I do really like this definition of it though. Chemical decomposition by water. So you have to add a water. So H2O in this case is going to be a reactant, and by doing so you can decompose the large molecule, or you can break the large molecule into two smaller molecules. Okay, so a reaction which uses a H2O molecule to break a large molecule into smaller molecules, it is the reverse of condensation reaction. There's a catalyst for it, which is, I think it's actually not that hard to remember, is potassium hydroxide, so it's a strong base. Now, the catalyst for condensation reactions was sulfuric acid, which is a strong acid. So the reverse of that is a strong base. However, this is a little bit confusing because I think you can use an acid for hydrolysis catalyst as well, but this is just a common catalyst. All right, let's use this. So I need to draw a reaction for the hydrolysis of butyl-ethanoate. Do I have two examples? No, I only have this one. So butyl-ethanoate. So you can start by drawing out the ester. You know it's an ester because it ends with OH. It's up to you. What I tend to do normally is I start with the ester linkage. It literally does not matter whether you draw it like this or like this. Either form is fine. I normally do this form. However, I think the other form will probably make it easier for the name. So with an ester name, this part is the acid part. So this is the acid part. Already has a carbon, so I need another carbon. So that's ethanoate. Butyl just means 4 carbon on the alcohol part. So 1, 2, 3, 4. 1, and then add the... Oh, this is not going to work out too well. Okay. Sorry, I just realized something. I'm not going to have enough room, so I'm going to have to do it vertically. So let's start again. We're going to have C double bond O, and then O, CH3, and 4 carbon. Okay, so 1, 2, 3, 4. Okay, now because this is hydrolysis, the other product has to be H2O. So if you want to, and I think if you have the name of the ester, you know what the two reactants are supposed to be. But essentially, in order to form hydrolysis, you need to decompose it. So you're going to break the bond here, essentially, because this part originally comes from the acid, and this part originally comes from the alcohol. So the OH in the water is going to be linked back to this C. Oh God, what is that? Okay, so it's really the O. the O is going to come back here, and this H is going to link back here. So what you're going to have is ethanoic acid. So I have the C with the 3 hydrogen, still C double bond O. So this part just come from the ester. 1, 2, 3, 4. Hi. So, how's everyone's holiday? Okay. I'm gonna make more small talk if I have to draw more carbon. So. This OH coming in here, and that gives you the carboxylic acid left. You can see the carboxyl group has been reformed. And this H comes in here, so the hydroxyl group is reformed. So you're going to have ethanoic acid and butane 1O as the products. KOH catalyst here. So that's hydrolysis. Actually very simple. It's just the opposite of condensation. Now, just to make life a little bit harder for everyone, let's talk about chance esterification, even though I need a data book and I can't find one, because I do need to... Where is my data book? Oh, here. Okay. So I don't know whether you remember, but chance esterification, we actually briefly touched on this at the start of the year when we talk about biodiesel. And chance esterification is actually a hydrolysis reaction followed by a condensation reaction. So let's talk about this again, because I think now it's high time to revise fuels. Okay. If anyone remember what biodiesel is, that would be great. But biodiesel is an ester. It's a methyl ester. So it's an ester that's made between methanol and a fatty acid. Now the fatty acid came from oil, which is the main, or you can also use animal fat. So basically fat or oil is going to give you the fatty acid. So there are two processes, or two steps involved in the chance esterification process. So the first one is going to be the hydrolysis of lipids, so fat or oil. Now the specific type of fat or oil that we're going to talk about is what is called a triglyceride. So this is your fat or oil, and we're going to revisit this one more time when we get to lipids. But it is a triester, if you will. Triester. So it has 3 ester groups in one molecule. So I'm just going to give you an example. There are multiple different types of triester or triglycerides that you're going to see when we get to the lipid topic, but this is just an example. So it is actually a very oh, perfect. I do have 2 slides for this. It's a very interesting molecule. So you have what is called glycerol, which is a diol, and the diol is going to form 3 ester linkage with 3 fatty acid. Okay, so this is the alcohol part of the triester. And then you have a C double bond O. Now, just because a fatty acid has like 15 carbon, I'm not going to draw that part out. So I'm just going to draw C. Let's just use what looks good. Okay, palmitic acid, so C14H. I can't actually do maths, right? 28 CH3. So this is just the remaining hydrocarbon chain. I'm really lazy, so I'm going to use the same thing 3 times. So CO double bond O and then C14. So this is definitely not structural formula. You will never be asked to draw the structural formula of this, because I don't think anyone has time to sit there and count 14 carbon. Okay, 28 CH3. So this is a triester. There are 3 ester groups present in this molecule. Okay, so the first step of chance esterification is hydrolysis of this triester. So I need to supply 3H2O, some acid, sorry, some KOH, for example, as the catalyst. And what is going to happen is you're going to break all 3 ester linkage. So you're going to end up with glycerol, which is a diol, sorry, a triol. So there's an OH here. OH, H. So the hydrogen in the water is going to be linked here. So you have a triol. This is actually called glycerol, which you can use to make soap and some other things. And the C double bond O is going to reform the OH. So you're going to get 3 of this thing, which is, I'm just going to flip it. So CH3, C14H28, COOH. So the first step, hydrolysis of fat and oil, producing 1 glycerol molecule and 3 fatty acid, which is still carboxylic acid. Now the second step of trans-esterification is the condensation reaction to make biodiesel. So each of the 3 fatty acids that we just produced before can undergo this condensation reaction. So let's say we have CH3. I'm just redrawing the whole thing, or rewriting the whole thing as it is. I'm going to draw the structure of COOH out just so that it's easier to see. So this is the fatty acid that we produced earlier from vegetable oil. You're going to react it with methanol most of the time. You could also use ethanol, but people tend to use methanol. I'm not going to explain why at this point. Well, you need H2SO4 catalyst. I explain why when we get back to school. So the product, once again, is going to be an ester. C double bond O, O, CH3. Now let's draw it out. And you're also going to produce H2O. So this molecule, which is a methyl ester, so it's an ester that has methanol as the alcohol counterpart. The acid part varies depending on which fat or oil that you use, but this is biodiesel. So that's trans-esterification. It's basically a hydrolysis followed by a condensation reaction. Okay, so the organic pathway of this, if you have alcohol and carboxylic acid, combine. So we have H2SO4 catalyst. This is a condensation. Then you can have an ester. Now if you want to reverse the process, so you want the arrow going back to these two, then is hydrolysis, and the catalyst is KOH. Okay, and that is that for condensation and hydrolysis.